I haven't I haven't actually felt very like swamped yet.
Interesting. That's a first. Usually, all right, maybe it'll hit like towards the end of this week. I don't know. But that's good. That's kind of reassuring. I don't know if that's the case for everyone, or if it's just Andrew. But yeah, usually at this point in the program, people are starting to get like a little, like the water's coming up to here. It's like, it's like starting to get a little hard to breathe. I'll be honest. I'm a little worried about you guys. Because like, what is it? 1, 2, 3. 1, 2, 3, 4, 5. It's been like 5 days since our last lecture, and no one's reached out to me, and that definitely concerns me. It's kind of weird because like usually the group me is like popping, but like nobody has also used the group me or anything, or I don't even know if you guys are on the group me. Um, I'm pretty sure. I mean, Sukmi's a new student here, so I think he needs to get on.
And I just joined
Oh, okay,
just
cool.
right before this class.
Oh, nice, nice. All right, yeah. So it's like no one's like really using the group me. Like communication's very lacking. And I don't know. I don't. It's either okay. It's one of two things. It's either you guys are like savants and like amazing at calc and don't need any help or whatsoever. Because I've been asking around too, and it sounds like you guys aren't taking advantage of the tutoring stuff too, or you guys are like super prideful people and don't like asking for help for one reason, whatever reason or another. I'm telling you guys, like we are meeting, we're lecturing, we're doing this thing for like 1 hour, like a day, and I'm telling you, it's not enough. You can't expect to absorb all the calc stuff in this less than 1 hour that we have together. So I don't know what your guys' plans are to get through this program, but I'll say it over and over if I have to, but you can't do what you did in high school and assume that you're going to get a good grade after it. Like if you maybe, let's say like in high school, if this is the way you kind of worked and we were able to pull off A's, then in college those A's will turn into C's, easy. So I mean, if you're okay with that, then I'm not okay with that. But if you're okay with that, then I mean, I can't stop you, right? You're the study habits and all that stuff, that all falls on you guys. Responsibility and all that jazz. All right. Even things like keeping your camera on. I've been asking you guys to do that since day one. And still some you guys are really like fighting me on this with the camera thing. When it comes quiz time, when it comes midterm time and final time, if you don't have your cameras on, I'm giving you a 0. That's like how it is. So you might as well just like get used to like keeping it on. And like I said, I do have like an understanding point of view on this as well. If you can't for like a couple minutes, you got to get up, use the restroom or whatever. Like I don't care. Like go ahead, turn it off. You don't have to ask or anything like that. That's fine. But if you're keeping it off the whole lecture, I'm assuming you're not paying attention. That's okay. Oh, but I'm gonna I'll leave stuff in the chat. I'm just like, all right, okay. But like, it's easier to just kind of talk to me, than to have for me like waiting on you to like say something in the chat. You know what I mean? So please, like, the more involved you are, the less like this you'll feel. And this goes across the board in all your classes. All right. That's enough. That's enough lecturing. All right. So let's talk about what we got to talk about today. It's lecture 4. Oh, Sukhmeet, at the end of the lecture, I'm gonna ask you to share with the class. I did this with everyone. Everyone has shared already. Share something like interesting about yourself. It could be like, I would say like on the weirder side. I think the weirder it is, the better. If you have one already, like ready to go, by all means.
Let me think about it.
All right, fine. But somebody hold him accountable. He needs to share with us. Okay, we all shared, right? We got like beatboxers and weightlifters and oh my gosh, interior designers, and I'm gonna cheat. Big jacket wearers and step counters and drummers and people that are bad with directions, people that lick their elbows. Me personally, I abhor coconut. It is disgusting. I know I'm forgetting a couple too. So please share something weird with us so you can be a part of this weird group here. All right. For today's class, I just wanted to remind you guys, we have homework 3 due tomorrow. I've been hearing from Gina. Some of you guys are not staying on top of your homework stuff. How's the homework been? Are they, is it difficult? Is it too much? Like what's going on with the homeworks? Some people aren't here.
Honestly, I don't think like the difficulty is the issue. I feel like it's a good difficulty, like enough that it's challenging. I feel like it's just like so many of them.
I feel like, yeah, I kind of feel like that. Like the concepts aren't hard, but some of the problems are really tedious. Like there's a lot of steps.
Yeah, I agree. I think that's the point. I think we want you guys to kind of like struggle with these homework problems in kind of a weird masochistic way, yeah. But yeah, but conceptually it should be in line with like kind of what we're talking about and stuff like that. So yeah, that sounds about right.
Yeah, for me, it's like there's always a couple problems that I just like get really stumped on, but usually I understand most of them. And like I guess at first, like especially with like the first homework and a bit with this one, the real problem I was having was like just getting the textbook to load for me. You know,
Oh,
like the
man.
PDF to load. It's just been like
Still having
like-
that issue?
yeah.
dude,
So like I finally like I had to like clear up space on my computer so I could just download it, and it's been like a little easier.
Dang.
But yeah, that was like being really annoying. Like
yeah,
for a
if you
while.
download it as a PDF and then like just find an app to like download it to. You can also like look up the pages because like also like the way like Tina gave it to us, like you can't look up the pages. So like if you download it to like any app that's meant for it, like it'll let you like look through
You're
pages. that
right.
aren't
Yeah,
downloaded.
you're right. Because it was shared as a Google Doc, right? So you have to.
Yeah,
scroll
that's what I
through.
finally ended up doing, and now it's pretty smooth.
Yeah,
But
like
like,
Okay.
you have to scroll. So like we started at like 6 point something, and that's all like already at like page 300 and something. So you had to like the first time I went through it, I had to scroll through like
Yeah,
30
my
pages
bad,
and
my
then
bad. Yeah,
download
so
it.
I think you guys should probably just find some space
Oh,
on your
yeah, like,
computer or something like that, and
just download it to any app. Most
Yeah,
apps
yeah.
like just have a thing for it.
Yeah. Speaking of technical issues, I've been also hearing, or I've been reading in the chat, that some people are having issues with like turning stuff into PDF. Are we still having issues with that or what? Do you guys know what we expect now from the homeworks that goes? It's the same for the quizzes and the midterms and stuff like that. So it's like, hopefully the homework uploading stuff has been practiced for the quiz tomorrow. Okay, so please make sure you have a reliable app for you to create your pictures into PDFs, because that way it makes the grading on our end smoother, and it makes in turn your responses a lot better, because otherwise you have to like click and have it to load and do all this other stuff. I had to download a freaking HEIC converter thing. God damn, I hate that stupid. Oh, anyways, so yeah, please make sure like your files are properly uploaded, okay? Because I know for a fact there will be professors that are super nitpicky about that stuff too.
So
give you a 0 if you don't even like upload that stuff correctly. You know what I mean? So
for the homeworks, is the picture fine?
that's up to Gina. I think she's been requesting PDFs, if I'm not mistaken. If you've been doing pictures.
Where
Yeah,
is homework number 3 posted?
What do you mean?
yeah, I was also wondering about that because I didn't see it in the assignments
Which
yesterday.
problems? Yeah, it's not under assignments.
She forgot to post it.
We had lecture 3, right? So there should be a homework 3 out. If someone wants to just shoot a message in the chat right now. Did she not post it?
No.
Okay, I don't know. That's kind of like on you guys too, to like the homework is, and the recitation stuff is her. That's her responsibility. So definitely reach out to her. If she didn't post, she should be posting it. What is it?
After class on
After class,
recitation.
right? Yeah. So she should be posting it, right? Because they're due at the start of each recitation, and then she assigns at the end of each recitation.
Yeah.
So definitely, yeah, send her a message if you guys didn't get one. I don't know. She might have to push the due date then. So for that one. All right. But yes, quiz 1 is tomorrow. Quiz 1, it covers everything from lecture 1 to this lecture, to this lecture, to this lecture. So y'all need to pay attention, because the stuff that I'm about to talk about today is going to appear on your quiz tomorrow. All right. Any other questions or issues before we get started? Today's lecture shouldn't be too bad. Well, okay, I don't want to say that. Today's lecture shouldn't be too long. So if there's time at the end, you know, I can talk about like what's going to be on the quiz and stuff like that, and give you guys a heads not a head start, because you guys should already have been studying, but like a heads up for your quiz tomorrow. All right, but do we have any questions from like lecture 3 with the integration techniques? I saw it's really weird, guys. I see the view counts. You know, it's really weird that I'm getting more views on the lecture 3 video, or no, the lecture 2 supplementary video than lecture 1 supplementary video. You need both. I'm just saying, because both are going to appear on your midterm. So yeah, if you're still behind on the supplementary videos, I didn't post one for the third one, so it's like there's no reason for you to be. So yeah, please make sure you're on top of that. But any questions about the integration techniques? So that means like things like you should know how to use sub, you should know how to integration by parts, you should know how to tabular method, you should be able to know how to do the grid method. If you have no idea what I'm talking about, then that tells me you didn't watch the video. You should know how to do trig substitution. You should know how to do improper integrals. I should be writing this down. Sorry. So integration techniques.
Sub, tabular method, integration by parts. Those are the first 3, first 4. I think I forgot the first one.
Yeah, I think I started off with USub. USub, I
Yeah.
actually didn't even talk about in this class. I'm assuming that you guys know how to do USub because that is a Calc AB material stuff. So
that
if you
again?
don't know what USub is, learn how to do USub. All right, that's the backwards chain rule. And then we learned integration by parts, which was 7-1. And then the 2 weird cases with integration by parts was tabular method. And the other one was the grid method. That was my shorthand, but that's the repeated one where like the original problem reappears in your work and you just kind of like swing it over to the other side and divide by the constant. If you have no idea what I'm talking about, oh gosh, you are in trouble. After integration by parts was trig sub, right? There were those 3 cases, right? If it looks like a squared minus root a squared minus x squared, root x squared, or I guess plus a squared, and then root x squared minus a squared, right? No?
Yeah.
Okay,
That
what are
was in
those?
the homework too, right?
I'm sorry?
That was in the homework too, like at the end.
I think that was the supplementary video for lecture 2, right?
Yeah, no, I was like the examples like doing the trick sub was in like the homework that was due yesterday.
We had a question that had.
Yes, I believe so, yep. Question? What?
We had a question that had that as well. So.
Oh, okay, yeah, exactly. But yeah, trig sub, right? This should be the thing where like after you make the substitution, things gloriously cancel out, right? Leaving you with like a semi-simple thing to integrate. Then you get to your final answer. You might have to draw a triangle to figure out like the resubbing back in for X and all that stuff. So look into it if you haven't. What else is there? So there's use of, partial fractions. We talked about partial fractions, didn't we? I feel like that was like a lot of what we did in lecture 3 or lecture 2, lecture 3.
Yeah, we talked about partial fractions and we did it with Gina yesterday too.
Awesome. Yes. So partial fractions, right? I think for this class, there might be one question where there's 3 factors on the bottom. I need to double check. Did she do one of those with you guys or no? Oh, she did. Wait, when there's 3 factors on the bottom? Okay, some of you are saying yes, some of you are saying no. Okay, Jeremy changed his mind. All right, cool. Yeah. So yeah, be ready. You got to be able to do one with like 2, one with 3, and I think that's it for this class. For the fall, they go into crazier partial fraction stuff. Yeah, it gets crazier, by the way. So just letting you guys know. Is that it? Integration techniques, use of integration by parts, trig sub, partial fractions. Which one am I forgetting? I think that's it. Right. Oh, well, okay, so this isn't an integration technique, but it is something, improper integrals, right? Improper integrals. That's basically when one of your bounds is infinity, or you go into like an asymptotic region where like the graph goes off to infinity and you have to calculate in quote unquote infinite region. Yeah. What's the one thing to remember with this, like with this thing, like in terms of notation?
Always to write the limit on every line.
Yeah. Thank you so much for saying that. Who? Andrew? Andrew, what do you look like? Can I just see your face, please? Just for 1 sec, just hit the video like and then hit the video real
All right, I'll hit it real quick.
real quick, I just want to see what you look like, because you've been,
It says no device was found to no video device was found.
damn it. Damn you, technology. Oh, I'll never know what he looks like now. It's so sad. Anyways, what was I saying? Oh yes, so improper integrals, right? Please don't forget the limit sign. Don't forget the lim sign on each step. I will take off, I'm sorry, I'll tell Gina to take off points. I think she's gonna grade the quizzes. We haven't really talked about that yet. But whoever's grading it, they're gonna take off points if you don't have the lim sign on every single step. Understand? Don't test us, we'll do it. But I think that's it. That's a big chunk of your quiz tomorrow. All right. The first chunk of your quiz is like the chapter 7 stuff, right? Areas under the curve, volumes of revolution. I don't think that there is a cross section one on there. I'm not 100% sure. Let me just double check. Yeah, there's actually, that one's going to be on your midterm. All right. So it's just finding area under the curve, finding, oh my gosh, computing the area, right? Sorry, no, I said that right. Finding area under the curve. Oh, and then like rotating stuff around a certain axis. That's gonna be on there. This stuff with the integration techniques, and then the stuff we're gonna talk about today. Cool. I basically just told you what's gonna be on this quiz tomorrow. I'm like looking at it right now. Okay. All right. All right. Let's get to what we got to talk about today. Man.
Can I ask why do they make us do the like equation and then wrap around the axis?
The what, I'm not sure what you're talking about.
Like when they'll give you an equation and say, like, if this equation was like rotated around the x-axis, what's the volume of that?
Why do we do that? Is that what you're asking?
Yeah, like what's the significance of how would that pertain to like the real world?
How does that pertain? I'm sorry, I just can't. You're like breaking.
How would that pertain to the real world? Like, what's the significance of us doing that?
Volumes of revolution, modeling purposes, I would guess. A lot of like, you guys know what 3D printers are, right? You guys aren't that young, right? Okay, so yeah, 3D printers, that's exactly how they work. They go slice by slice, figuring out a certain region and then just layer it on top of each other for a certain amount of bounds, right? I guess they're going dy instead of dx, but that's just one example. But really, modeling purposes, you can make a lot of stuff, like a lot of 3D rendering software is like a big thing, so it's like a lot of that stuff uses those ideas as well. If you know the cross section of the shape of something and then just kind of like spin it around a certain axis, you can generate a picture or a 3D model of something, if that makes sense, right? And then like in Calc 3, they use this idea to do like, don't forget, but they do like double integrals and triple integrals, and those are the worst. I hate them.
What's a double integral?
You'll find out. All right, so for today, we're talking about differential equations, right? I always forget to put the page numbers in because you guys never remind me. But if I write down like a page number, I'm referring to the PDF page. So it's like you type in that number, it'll bring you to that page. Yeah. So 515 is where 9.1 starts because we were just on chapter 7. We skipped chapter 8. I don't even remember what chapter 8's on. And then we're just going to jump to chapter 9. We're going to be jumping around again to chapter 10 after today, I think. And then we jump to like 11. I think 11 is sequences in series. So yeah, so we're gonna go to 515. That's chapter 9, and we're talking about something called differential equations. Do you guys remember what differential equations are or were in Calc 1/AD? Off to a great start here. No, we don't remember. Okay, do you guys recall this notation? If you have like dy over dx is equal to, let's say, x equals x plus y.
Yeah.
Okay, Orange says yes. And like, do you remember anything about this? Like, if you had an equation like this, like equals x plus y, what it represents, what it means, or anything like that? All right, cool. So please pay attention. So it's essentially, there were a couple of ways you guys represented this in Calc 1. One of them being slope fields. Do you guys remember that? So it was like when they made you like with those like dots and stuff, and then like they made you
Yeah,
like,
I remember slope fields.
What's like the Maxwell equations? Like just a bunch of arrows.
Yeah, they were like a bunch of lines, right, on a coordinate plane. And essentially what they told you was a slope at a specific point. And in fact, that's like the definition of a derivative, right? I know it's been a while since you guys have dealt with derivatives, but this notation is essentially, it's like the derivative, right? It's the change in y over the change in x at a given defined x comma y. No, yeah, kind of, sort of. So this is called slope fields. And what was a slope field? It was just a sort of visualization. It was like some sort of visual representation of a differential equation. That's essentially what it was, right? What is a differential equation really? It could be a whole bunch of stuff. It's just a function that shows like the rate of change at like any given point. I think I'm like really loosely defining it here, but I feel like that's like the best way for us to kind of grasp it. Let me share my screen right here to show you guys. All right, so this is the example that I was just playing with, right? X plus y. This is an example of the slope field, not the green piece, okay? The green represents what's called a particular solution. Excuse me.
So like, does that mean like if you were to, if all those arrows were the direction like A is gonna go, if you put it like on one end, we would just go to the other end?
You're coming in like fuzzy. Can you say that again, Alan?
So like if all those like arrows were the direction it was gonna go, and you put like a ball like on one end of that green line, right? Would it end on like would it end at the other end of the green line? Would it like go to the other end of the green line?
I don't know what you mean by arrows.
All those little lines.
All these little lines represent slopes at those said little lines. That
Yeah,
at those
so-
points. So for example, real quick. If I highlight 1, 1, that point right there is 1, 1, correct? If I plug 1, 1 into my differential equation, what do I get?
Nothing.
Huh?
You don't get anything if you plug
2.
one.
You get 2. What's 1 plus 1, right? It's x1
well, yeah,
plus
2.
y1, right? So you get 2, which means the slope at 1, 1 is 2. Do you guys see? Does that make sense? Does that resonate? And you can see that, right? The slope here at 1, 1 is 2. Does that make sense? And that's how you generate all of these tiny little lines, right? I don't like, they make the lines at like nice whole numbers. You can make the lines everywhere, right? I could have chosen 0.3 and 0.7, right? And I would have gotten a slope of 1, right? So that means at 0.3, 0.7, there should be a line that looks like that. You know what I mean? They're just choosing nice numbers.
But like say it was like this graph represented like north, south, and west and east. Like it literally was just like these directions are exactly like how it looked, and right, the physical quantity or the physical thing you're looking at is behaving exactly like this. Does that mean that if you put something like at 4, -5 or -5, 4, sorry, that it would end up at like just at the end of the line?
End of what line? There's a lot of lines on here, buddy.
Oh, the like third line, the green line.
You're talking about the particular solution.
Yes.
Okay, hold on. I haven't gotten to the particular solution yet. That's why. Okay, I think that's why we were confused. I'm talking about big picture here. Okay. All right. So what this generates, okay, what this generates are possible solutions or particular solutions, right? So I think what Adlin was saying was, if I wanted the graph that goes through, I think he said -5, 4, right? It actually does in fact generate the green line, this green function here. All right. It's like, the reason why they call it a particular solution is because it's the only one that will work. And the way it's generated is you use like the neighboring slopes to kind of dictate the behavior of, I don't know, I think you said a ball or something like that, right? So yeah, if you like drop the ball in this thing, the route that the ball would take, it would essentially be the particular solution. That's an interesting way. I've never heard it like explained like that. So
For some reason, it kind of reminds me of like the game of life.
a what?
Like the game of life, the program made by the mathematics, like, that 2020. You can look it up, like in Game of Life, this is a program, it's a way to.
Okay, I've never heard of it, but okay. Sure. So, that means so right now, not the computer, the program, this program right here is, the input is the initial condition. It's called the initial condition, is 2, -1, which means give me the graph that goes through 2, -1. However, if I move this, what do you guys think is going to happen? If I move this from 2, -1 to like somewhere over here, like, what is that going to change? What's that going to like dictate here? What do you guys think?
The end result. Everything, the path and end result.
The path? Okay, cool. All right, so watch. I'm going to move this particular solution to -2, 4. What do you guys notice happen?
Nothing happened.
Nothing happened. Nothing at all. Is this function the same function as before?
Oh no, but it's smaller. But I mean, well, it's moved, not smaller. It's
It
moved.
is, shape wise,
Whoa.
it's the exact same function.
No.
What do you mean? Like it's.
The other
They changed the
function looked like
particular. It's a
this. It was
different
at
function.
2,
Yeah, it
-1.
was at a different location.
What?
It's a
Like,
different function, but it
the
still
path
follows the
changed.
slope field.
It's still okay. All right. Yeah, that's what I'm saying. So what I'm saying is the one that we just drew is like it looked like this or something like that, right? This pink one is not the same thing as the green function. They're not on top of each other. You can't say that they're the same function. They came from the same differential equation though. So thank you for that, Justin. I appreciate the clarification. All right. And how do we generate these? Once again, you're just using neighboring slopes. So if I started here and I'm looking at the tendencies around this point, I'll change the color. If I start here and I look at the neighboring tendencies, that's going to like dictate how it's going to behave. So this one should look something like that. And the one above, the slopes above it are kind of like going like that ish, right?
I think,
Just a
yeah, I
guess.
think it stayed the same because you moved it to like you moved it to a point that had the exact same slope as where it was. Like the shape stayed the
The
same.
shape stays the same. Okay, sure. Yeah, that sounds about right. But if I move this over here now, right? You see how it's using the neighboring slopes. My graph is obviously off, but it was a rough estimate, right? I was close, kind of, right? But yeah, it's using the neighboring slopes. Thank you, Jeremy. By the way, I see you, Jeremy. Thank you so much for doing this. It means a lot to me. But I'm using the neighboring slopes to dictate the green behavior. All right. Yes. Okay. So we're good on the visualization. We kind of get what's going on here. Oh shoot, is Ozzy in? I let Ozzy in, right? Is he here? Oh yeah, okay, good. So going back, we're gonna now solve differential equations. As in, we're gonna look for these particular solutions, these green lines, right? Given a certain differential equation. Make sense? However, we're gonna run into a problem. Watch. So the example I was just playing with, x plus y. If we want to solve a differential equation, okay, we're actually going to need to integrate both sides, right? Think about it. We're given a derivative, right? The dy dx is equal to x plus y. Well, that means we can integrate both sides. We can, algebraically speaking, we can integrate both sides, giving us a particular solution, right? I think the first initial condition, that the point that we go through, it's called initial condition, sorry. But the initial condition we used was like 2, -1 or something like that. I think that was one of the first ones we used, right? And we can use the initial condition to get to a particular solution. Yeah, are you guys catching on the jargon? Right? So let's try it. Let's try to integrate both sides. Ready? Okay. So, well, it seems like I have a couple of pieces flying around here. I got some stuffs with y's. Stuff with y, and I also have some stuff with x's. Yeah, well, if I kind of put it together, if I put those two pieces together, I can integrate them at the same time, right? One side in terms of dy, one side in terms of dx, and actually get to something, right? But we're gonna run into a problem here. Watch what happens. How do I move the dx over to the other side?
Multiply both sides.
Who said that? Was it Warren?
Shouldn't you subtract y first?
Oh, so we have Who's a battle? Who's the first person that said something?
That was me.
Oh, it's Dan. Okay, so Dan says let's multiply everything by
Yeah.
dx. Oren though, she's like, wait, no, let's subtract both sides by y. Fight, 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 fight.
It's a non-separable equation. So
Oh, Dan,
we can't
come
integrate both
on,
sides.
man. You can't just ruin the surprise like that. Did you guys hear what he said? Oh no. All right. Dan, shut up. Don't ruin the surprise.
I heard it.
Damn.
I heard it.
Damn. Okay. All right. So I was gonna torture you guys a little bit. I wanted to incite some fighting, have you guys like actually talk a little bit for once, but I guess we're not into that today. So yeah, this is actually called what's called a non-separable differential equation. It means I don't know why I put an S. It means that you can't, by the rules of algebra, you can't move the dy's and the y's onto one side, the dx's and the x's onto the other side. Watch, if I subtract both sides by y, I get this, right? And then if I multiply everything by dx, well, what's going to happen algebraically? Like, what do you see? What's wrong with this picture?
You have dx on the side of the y.
Yeah, and no
there's
matter
nothing
how you move
right
it
there.
around, exactly, no matter how you move it around and stuff, you won't ever be able to separate the y's with the y's and the x's with the x's. Hence, it's non-separable. That's why it's called a non-separable. Okay, so there's a really, really easy trick to figure out if a differential equation is separable or non-separable. If you're given something with a plus or a minus in between your x's and y's, it's a non-separable, because this will always happen. Does that make sense? Algebraically speaking. Yes?
Yeah.
Anyone have
Is there
questions
any
on that?
is there any like case where that's not like the case, where like x plus y could be, or is it always just like
Just because of algebra. Just
Like, if you
algebraically
had, say,
speaking, if an
like-
x and a y are being separated, like it's like a binomial or something like that, you can't separate them.
if there was a polynomial, I should say like x plus y in parentheses times x outside the parentheses? If there was
What?
something to that, like if you start like adding just like x exponents, like would it eventually become, like would you eventually look at something that does have this that would be separable? Or is it just the x plus y, if you ever have that, it's automatically like a non-separable?
I'm not really, I couldn't really hear
So,
the
like,
first thing that you were
If
saying.
like say the x and the y were in parentheses,
If
could
the
you,
x
like,
and the y,
add-
okay, what I'm hearing is if the x and the, if the x and the y were in parentheses, like that.
could you add an x outside the parentheses and eventually like theoretically just add enough x's that it's separable? Or not add, like multiply.
Okay, which one is it? You're saying add and then multiply.
I mean multiply, sorry.
If you multiply, then you get x squared plus yx.
Mhm.
This is a non-separable because
It's
you have
still
an x and a y being like added.
So
to
it's just that factor is always non-separable. That like specific, if you can ever break it out into those parentheses, it's a non-separable. If you can ever separate x plus y into a parentheses like that, it's just a non-separable. I think I'm
So
asking.
I'm still not sure what you're asking, man. I'm saying if you have x's and y's, if you have
So
some
if
x's
any-
and y terms separated by a plus or minus, it's a non-separable.
Okay.
Okay.
Yeah, I was just asking because you're not always going to see it like x plus y, but if you can like get it to, like if you can get your parentheses, like like how when you see x squared plus blah blah blah, and you break it down into like two parentheses.
I'm not really sure. It sounds like you're saying to break down a quadratic,
Like
but
Yeah.
differential equations can include both x's and y's. It's not always going to be just y's. It's
Yeah,
not always going
but
to
if
be
it's-
just x's.
if it's plus, if it has that plus like in between them.
Right, yeah, so I was
And
saying,
if
if
you
there's
ever
a
get
plus
like-
or minus between some x term and a y term, then yes, it is a non-separable. That's what I've been saying.
But not minus.
What?
If it's a minus sign.
Yeah, addition is the same thing as subtraction. You guys know this, right? It's the same operator. You're just doing a negative, right? Okay. All right.
So
All right. So let's do a separable differential equation, okay? The first one was meant to trick you. The second one is going to be a separable differential equation. Now I screwed this up last year. I double checked this. I'm pretty sure this is the right one. So here we go. How do I know that this is a separable differential equation?
There's no plus or minus sign between the X and the Y.
Yeah, where'd that come from? Yeah, thank you, Jeremy. Love the enthusiasm, right? X and the Y, they're being you can say multiplied or divide, right? Multiplied by the reciprocal or divided. But yeah, they're not separate. This is a singular term. Maybe that's how I should have said it, right? It's a single term. The other one, there were two terms, right? So on this one, we can actually now separate our X's and the Y's, right? I'm gonna do this real quick. It's just move. I'm gonna shove all the Y stuff to the left, all the X stuff to the right. So that means I'm gonna multiply both sides by Y, multiply both sides by dx. Piece of cake, yeah? Just a heads up, not all your problems are gonna be this easy. I'm just letting you guys know. And then so that's step one, separate variables. Oh, so I forgot to give you an initial condition. Let's say 4 commas, let's say 2 comma 10. Oh my gosh, whoops, sorry. Initial condition is 2 comma 10. All right. By the way, you can't find a particular solution if they don't give you an initial condition, right? That should make sense. If I don't give you a point to go through on the slopey field thingy, you won't know where to go through, right? So you just gotta watch out for that. All right. Make sure you have an initial condition if the question asks for a particular solution. Here we go. We separate the variables. Second step is you integrate. Don't hate.
Integrate.
Yeah, there you go.
Yeah,
I
woo!
said it, but I forgot that I was muted, you know.
Oh my gosh. All right. Yes. So once you separated the variables, you integrate on the left side. So it just turns into 2 integral problems. The left side becomes y squared over 2. I'll explain this in a second. And then the right side becomes negative x squared over 2 plus c. Why didn't I put a plus c on the left side? I don't get it. There should be a plus c that comes out, right? That's what my math teacher told me. There always has to be a plus c that comes out.
You don't need it.
Yeah, because it's a Y, so you don't need it.
Oh no.
You could just move it over.
Thank you. That's
Yeah,
my
yeah.
reason, okay. It does
They're both
need
constants. Yeah.
it does need one. Both of them will spit out a constant, but with any equation, you can move stuff over. So I kind of did it without telling you guys. You can move the constant over to the other side, and it just becomes another constant. Make sense? So it's just that 1 plus c is going to account for the plus c's that came out. Yeah. And did I lose anyone on that? No?
Nah, it makes sense.
All right, thank you. All right, and then from here, we're almost there. I need to find a particular solution. Excuse me. So I need to figure out a y equals, right? A function, an f of x. So let me solve for y. So let me multiply everything by 2. We get what happens if I multiply a constant by another constant?
Just a constant.
You get another.
You get
constant.
another constant.
Okay, and then here's the tricky part. And this is where a lot of people always screw this up. What happens if I square root both sides?
You have to plus minus the other side.
Yeah, you guys have to watch out for that. All right. So if you square root both sides, you actually get 2 graphs. This should kind of look familiar, actually. Some of you guys should be like, wait a minute, I think I know what that is. We don't want a general solution. If you have an answer that has a C in it, it's called a general solution because it's not particular, right? We need to plug in the initial condition. Oh, sorry. Step 3 was solve for y. I know some of you guys really like the step-by-step thing. That's why I'm doing this on the side. Step 4 is to plug in initial condition. So step 3 was to solve for y after the integration step. Step 4 is to plug in your initial condition. What did I say it was? Was it 2, 2? Was it 4, 4?
2, 2, 2, 2.
Thank you, thank you. So we're going to plug in 2, 2. So in this case, it was 2, 2. In for x and y. What is that? That's 2 equals plus minus root c. Oh, right.
4.
Something weird's going to happen, but okay. So watch. We're going to solve for this. I want to solve for c. I square both sides. I get 4 is equal to. What happens when we square a plus minus?
It becomes
You got
positive.
the plus
It's like
minus.
a plus plus, right? When you
Yeah, plus,
multiply
plus.
negative on negative, so that plus minus actually just goes away. When you square the root, you get c minus 4. So c is equal to 8. Plug that bad boy back in. into, make sure you plug it back in the correct formula. It's this one. You get y equals plus minus root 8 minus x squared. That's it. That's how you solve a separable differential equation. I just threw out a lot of vocab in a very short amount of time. I know, like we talked about separable versus non-separable. We talked about general versus particular solution. We talked about, what was the other thing we talked about? Separable, non-separable, initial condition. We talked about, is that it? Whatever. But all in all, this is like essentially in a nutshell, how to solve a separable differential equation, right? But what the heck did we just solve for? Let me show you. I'm going to go back to this website and I'm going to plug in our differential equation. It was negative x over y. What are you doing, buddy? All right, there we go. Ignore the green piece. What does this look like to you? Can I move this out of here? Look at these lines. Can you look at the tendencies? Tell me, what do you see?
A field.
A field? A slope
Yeah,
field?
sure.
Okay, fine. It is a slope field. Thank you very much. What do you see in terms of like do you see a pattern?
Oh,
Yeah, I
I
see
see
a
like
pattern.
circles.
You see circles, right? You see circles depending on where you start. No? Anyone? No? What was our initial condition again?
2, 2.
2, 2.
2, 2. Where's that? That's about here, right? So if I follow this trend, I get a circle. Oh my gosh, that was so. You know what? I'm just gonna cut my losses. Where's that green dot? 2, 2, 2, 2, 2, 2. All right. The reason why it comes out like this is because the computer is not as smart as we are. Believe it or not, it like gets to an undefined slope and then just spazzes out. That's what's happening. But if you look, right, this looks like the top half of a semicircle. I mean, of a circle, a semicircle, right? And then if we have the bottom half of the of the circle, the bottom semicircle, right? That's why we have a plus minus in our equation, right? What do? We just found a particular circle within a family of circles. Right? Questions? Does the picture help?
So why does it look like that? Is that
Oh.
actually not what it's supposed to look like?
Why does the green look like that?
Yeah.
Oh, okay, because there's a little man inside this website doing all the computations and calculations, and when it gets to the undefined slope, it like just flips a table and is like, nah, bro, I'm done. Get me out of here. And he's
So
like,
is it
this is the
actually
little
a whole
man
circle?
trying to escape out of the computer.
So is it actually just a circle though?
It's supposed to be, yeah.
Okay.
It's the same
I was
thing.
like so confused.
It's the same thing. Have you guys ever tried graphing a circle in your graphing calculators, in your TIs? It does the same thing. It's because the
Does it actually?
computations, when it hits something over 0, it's like, no, bro, I'm not allowed to do that. So I'm going to freak out and does not compute error, it's going to do that and not. be able
But
to-
why
So
is
if
this
it's
the
like
solution
not
that
a
it comes up with?
function,
Whoa, I can't hear two people at the same time. Adlin, what?
Why is this the substitution that it comes up with? Like this is a weird looking thing. And it's also not symmetrical on either side.
All right, well, let's use kind words, all right? I'm sure it has feelings, man. Don't say it's weird. It gets like the top half of it, right? It kind of gets the top half of it, but like I said, as it approaches the infinity slope, it's not able to get the rest of it. Okay. Brandon, what's up, man?
I was asking if it was because like if anything is not a function, it'll just bug out.
Ooh, that could be another interpretation of it. Yeah, right. It doesn't pass the vertical line test, so it won't be able to,
Yeah.
I don't know how they program this thing. I really don't. Maybe you guys can figure it out. Oh, extra credit. All right. I'm gonna move on. So that is solving. What time? Oh my gosh, damn. All right, I gotta get to 9.4 real quick. Holy crap. All right. That was solving differential equations. I'll put another example in the supplemental video of how to solve. But if you need it, if you don't need it, then skip that part. Okay. But we're moving on to 9.4. 9.4 talks about a very specific case of differential equations. It talks about something called oh my gosh, logistic growth. If you guys took I think it's AP Bio. I think they talk about this in AP Bio. So if you took AP Bio or whatever, you should know what logistic growth is. But let me pose a question to you guys. You guys know this differential equation, hopefully. Oh, it's K is a constant. This is called a growth constant. Have you guys ever seen this before?
Yeah.
Okay, you should have. This was what you learned in Calc 1, right? If you separate the variables and integrate both sides, you actually get you guys know what that is? Oh, I don't know whether that D is there. I'm sorry. And A is your constant. A is like your like C value. K is still your growth constant. It's like a given, right? But what is this? Do you guys know what this is? Starts with
The
E.
interesting.
Interesting. Okay, fine. It deals with interest, but it's called
Exponential function.
yeah. This is exponential growth. You guys know what exponential growth is used for and stuff? You guys don't care. Whatever. It's okay. Whatever. Exponential growth. It has a lot of like uses in the real world, right? It's talking about population, talking about how money grows, right? Or interest, right? This is how money grows, right? And this is how things grow naturally in this world. It's like a naturally occurring phenomenon, yada yada yada. However, it is actually not a good model in the long term. Did you guys know that? Think about it. If you have cells that reproduce at infinitum, right? And you let them like, cause they're gonna double like over and over and over and over again. Wouldn't it like the number you get is gonna be 2 to the power of like a really big ass number, which is just not real. Like that means the cells would take over the entire world. You know what I mean? You guys never thought about that? No?
And you reach carrying capacities and stuff.
What is that? Was that Waldo? You guys are-
Yeah,
you guys are-
I couldn't hear you at first because like I got kicked out because my like computer completely shut down.
Oh,
But
that's
like
good.
I took AP Bio, so I know like about the logistic.
Yo, that's what I just said. That's what I just said. Oh my gosh. All right, I guess you missed that part. All right. So yeah, logistic growth, okay, to explain, is a better model for this. It's to take account of something called what's called a carrying capacity. So think about the cell example I just said, right? If I have 2 cells that are like reproducing, they can only grow as big as the petri dish. That petri dish is your carrying capacity, right? You guys ever see like in a room, right? Max capacity is like 100 people or something like that, you know? Like where do you guys think they get these numbers from, right? They have to model the finite amount of space that people can have in a room and yada, yada, yada. Well, when they think about other things like wildlife reserves or coming up with a pen for like a farmer or something like that, they need to know what is the optimal amount of like space and whatever you're trying to grow like that you can have. Does that make sense? So logistic curves, right? So exponential curves look like this. This is an exponential curve, right? It's gonna, but this is a, like I said, this is a bad representation over a long period of time. It's a good representation in a short period of time, but over a long period of time, this thing's gonna go off to infinity too quick. You know what I mean? Logistic curves account for this. And in the beginning, it's gonna look exponential, but eventually it's gonna act asymptotically towards your carrying capacity. Does this make sense? Does this graph make sense? If you were to look at this graph, where's the fastest point at which it's growing? Ooh.
The vertical midpoint.
The vertical midpoint. Okay, I'm assuming he means the middle. Yes.
Yeah.
Okay, the middle, right? The middle is where the derivative is the steepest, right? You can see that. So this is we use okay. Books use different letters. In BC, carrying capacity, they use M. I teach BC, so I'm gonna stick with that. I think in college they use something else. It's either A or Y or something like that. But I'm just gonna stick with M. Okay, so M is the carrying capacity. Yeah. So that means M over 2 is where it grows the fastest. Now, usually what I do is I prove the formula for the differential equation dy. Let me use dp over dt because p, let's say p stands for population, t stands for time. Okay. So the what I usually do is show you guys the proof for these 2 formulas, but there's no time. I'm gonna just do this in the video. Yay, we don't have to watch it. Oh. Right. So dp over dt for logistic curve. Okay. Just think, it looks exponential, So hence the KP, right? You guys see the resemblance, right? The KY. Yes, it's just P instead of Y. It has the KP, but it needs to account for the carrying capacity. So it needs M minus P.
Oh.
I swear, Jeremy's literally the only one that's been listening since lecture 1. Good God. Thank you, Jeremy. But yes, all right, it's KP times, and that M minus P, what that's going to do is limit how fast this thing can grow, okay? If you only have a certain roof over the amount of things that you're growing, it can't grow past the roof. It doesn't make sense. And if you start above the roof, right? Let's say I started above here, it has to come down to the roof. You know what I mean? So it's either way. The formula, the P of T formula, the population formula is a little, it's ugly. I'm going to show you guys, don't freak out, all right? Ready? It goes M over 1 plus AE to the negative MKT. I'm going to prove this in the video. Jeremy, oh my gosh, your face. Oh man, I'm gonna show this in the video. If you really care, if you really are like, whoa, that is one badass looking formula, right? And you're like, I want to know where that comes from. Watch the video. It's good. It's going to be a fun time, right? But if you really don't care, you're better off just memorizing these, right? I wanted to show you guys more graphs, but I don't think we have time for it. So let me just tell you guys, there's other like quote unquote forms, they're equivalent, but there are other forms of this formula in the book. Because like I said, these formulas are more like Calc BC. This is the one stuff I teach my high school kids, but in college, they might show you these. So you should probably write these down. Instead of it still does KP. One of them looks like this, like 1 minus P over N, which is literally like the same thing as the first thing. It just, they factored out an M into the growth constant. So the growth constant is like a little different. And the other one is these dy over dt is equal to ky 1 over y minus a. These all mean the same thing. These are all talking about logistic growth. So if you are able to identify the y, I'm sorry, not the y, the k, the growth constant, and the carrying capacity, you should be able to kind of plug in and figure out what the differential equation is, all right? And then from there, you can plug in to figure out the population formula too. So, you know, technically you don't need to integrate if you know the formulas. Damn, 5 minutes. I'm gonna go through one really quick example because these problems are super quick. If you know the formulas, Hey, that's not right. It's not 501. It's, I'm gonna update these page numbers. It is page. Let's do example 2. I'm on PDF page 541. We're gonna look at example 2. So example 2. The PDF page is 541. Right. So we're talking about deer population. So like I said, logistic curves are for realistically seeing how a population grows, right, over a certain amount of time. So the phrasing says you have a deer population. I'm really shorthanding this because of time. You have a deer population. It grows logistically. So that's how you know we can use these formulas, right? They give you a growth constant K is 0.4 per year in a forest, and the carrying capacity is 1,000 deer. Yeah. So the first question is, oh my gosh, that's supposed to be an A. The first question is, what is P of T? Find P of T if the initial amount of deer you start with is 100, right? So think about it. You start with 100 deer, they're gonna get freaky, right? And you wanna know how fast the deer are gonna grow over a certain amount of time. So we need the formula that fits that. Make sense? So we have an M, we have an K. So if you memorize the formula, which hopefully you guys are good at, it looks like this: 1 plus AE to the negative MKT. Well, let's look. I'm trying to find P of T. I have an M, I have a K. So what can I plug in to kind of solve for whatever? Like, what do you guys think we should do to solve for P of T? My function.
Plug stuff in.
Plug stuff in. Oh, it's always a good idea, right? I have a K and I have an M. So let's start there. Well, M is 1,000. So I'm going to start with 1,000. Do I know A? No, not yet. So I have an A. E is not a variable, right? E is it's 2.717 blah 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 blah, right? It's a constant. Negative 1,000 because once again we know M. Do we know K? Oh wait, we do. It's 0.4 times time. Well, I kind of whittled it down a little bit, right? I still don't know that A. Do I know one other piece of information where I can plug in for T though?
Isn't it a year? Is it a year?
No, I think you're referring to the growth constant, right? No.
Oh,
We already plugged
We
in.
know P initial.
P initial. What does P initial mean again?
What
That
you
at t
started
equals
with.
0, we have 100 here.
You mean at time 0, right? Not P0?
Yeah, sorry.
Yeah. Oh, okay. At time 0, you start with 100 deer, right? So we plug in 0 for T, we plug 100 in for P, and now we can solve for A. You guys see that? So we're going to plug 100 in for P. We're going to plug hold on. I'm just going to leave it at that because if I plug in 0 for T, it's going to turn the whole upstairs, that whole exponent to 0, right? So I can actually just kind of get rid of that. Yeah. Did I lose anyone on that? Okay. And now I can solve for A, right? I can multiply both sides by 1 plus A. I can divide through by 100. What do I get? That's 10 is equal to 1 plus A. And I get A is equal to 9. Am I done? Did I answer the question? Mohammed, what do I do?
What was the original question asking?
That's a good question. Though. You always want to ask that, right? What are we looking for again?
We only found A. So
Yeah.
now to plug A back in
Thank you.
instead of T with 0.
Right. So we're going to plug A back in. We're not going to plug in a T, right? Because that's what we're looking for, a P of T. So we found A. So we get P of T is equal to, my function is 1,000 over 1 plus not A anymore. It's 9. E to the, what is that? Negative 40 or negative 400? Is it negative 400? I'm going to say negative 400 T.
Negative 400.
And this is it. This is the function. If you graph this in Desmos, you're going to get something that looks like this, right? And then the top is going to be 1,000, right? But if you graph this in Desmos, this is the function that represents the friskiness of those deer. Sound good? Anyone
does
have
the-
questions? What's up?
What does A represent in the context of this question?
It's just, I'm going to give you an answer, Justin, that you're not going to like. It's the, watch the video. Watch the video and you'll find out. Okay, fine. No, I'll just tell you. It's the, it comes from, oh my gosh, when you integrate both sides, because guys, look, because what we did in the beginning, right? It goes back to what we were doing in the beginning of the lesson, right? Where is it? We start with this differential equation. We're going to move all the terms to one side and yada yada, and then integrate. And then things are going to get really crazy. But that A comes from the integration constant. That's the best answer I can give you. It does, in the context of a situation scenario, I can't really say, it depends on the scenario, but calculusly speaking, it comes from the integral constant. Okay, just like how this A comes from, oh gosh, whoops. This A comes from the integral constant as well. You know what I'm talking about?
Yeah.
Yeah, okay, cool. All right, shoot, I'm running a little bit over time. I apologize, guys. Do you guys have a class after this? No, all right,
This is the
cool.
last class for the day, and then we have tutoring later.
Okay, cool. Guys, please ask questions during tutoring. I don't want to hear that you guys are literally sitting there for 2 hours just staring at a blank screen and doing nothing for 2 hours. That's such a waste of time. At least like ask me for questions, like do something. Like don't just sit there for 2 hours and waste that time, especially when you have a quiz coming up tomorrow. You know what? Now that I remember, we kind of went over the quiz stuff. I kind of wanted to save 5 minutes to answer any questions about the quiz, but I feel like I told you guys everything that's going to be on this quiz, right? It was, if you didn't remember, it was the stuff from chapter 7, areas under the curve, volumes revolution, right? Integration techniques, what I'm showing on the screen right now. We went through that. And then literally this, solving a separable differential equation, right? Given an initial condition. What we just did here, not this one, that was the duped one. This one, right? Solving one of these and using the logistic growth formulas. Something like this example right here. I'm going to give you a scenario. You're going to need to find the dp over dt. You're going to need to find the p of t function. So get to memorizing those formulas. Okay. Any last minute questions before I let you guys go? No.
How long is the quiz?
It should take you about 40 minutes. I'm going to say it should take you about 40 minutes to do. So I'm going to assume that Gina's going to take the first 20 minutes to like review, or you guys can ask your questions or say your prayers, whatever. And then the last 40 minutes, you guys should have enough time to finish the quiz and submit on time. Please make sure you guys are submitting this stuff on time. All right. We don't want to hear the internet messed up. Don't blame the internet. You know you didn't submit it on time. Okay. Please don't wait until like the last minute to submit either. Okay. Give yourself at least like 5 minutes or so to submit. Okay. Any other questions? I will post a video. Actually, you know what? I'm kind of lazy right now. I'm just going to post the video I posted last year because we actually covered the same amount of stuff. The supplemental video will be, it'll show you an example, another example of solving a differential equation. And it should also show you, what is it? A logistic growth problem. Oh man, I'd be really upset if I did the that bastard. If I did whatchamacallit, the same problem. That would suck. Did I? Oh my gosh, I have to make a new video. It's the same problem. Damn it. Damn you, Past John. Okay, all right. I will make a new video with 2 examples, one with a differential equation, one with the logistic growth, and then the proof for the logistic growth equations, for those of you that are interested. I know it's like only 1 or 2 of you. All right, but definitely check it out for the first 2 examples. Okay, and please, guys, I know your quiz is tomorrow, but ask me questions, or ask Gina questions, or email me or something. Ask questions during tutoring. Yeah. Okay, all right. I think that's it. If you guys have questions, you can stick around. If not, have a nice day and good luck on your quiz tomorrow.
Bye. Have a nice day.
Thank you. Take care.
Take care, guys.
So Mr. Lee,
Sugmeet, don't leave yet. Don't leave, Sugmeet.
No, I'm here.
Oh, okay,
so
good. Yeah, what's
I
up?
refined my question, like about the x plus y thing.
Okay.
So like, you know how like you can start off with like an equation that doesn't